of bioactive food ingredients. And this one is a different topic, and it's my kind request to all the participants, listen carefully, because this one is a new topic to us, and discuss at the end of this session to our expert. Sir did his B.Tech from Andhra Pradesh Agricultural University, Rajendra Nagar, in agriculture engineering. Then M.Tech from IIT Kharagpur in dairy and food engineering. PhD from IIT Delhi in biochemical engineering and biotechnology. After that, sir was joined as a project engineer in Vanguard Indian Private Limited, New Delhi, in year 1995 to 1997 as a design of process equipment and project management. Then NDRI Karnal from 97 to 2006 as a scientist and scientist senior scale. Then in 2006, sir joined as a senior scientist at CIFET, Ludhiana. Then presently from year 2012 to till to date, sir worked as a principal scientist. Sir published so many books, then research articles, and also presented a paper in different conferences, international as well as the national. Sir published 55 research paper, then 6 book chapter. Sir patent granted 4 and 2 patent filed. More than 60 presentation in international and national conferences, and sir worked as a PI in different externally funded project. Then sir received so many awards in that: Fellow of National Academy of Dairy Science, Best Paper Award for a research paper published in Journal of Agriculture Engineering, Fellow of Institute of Engineers, ICR National Fellow, Fellow of Society of Applied Biotechnology, Commendation Medal of Indian Society of Agriculture Engineers, Research Team Award of Indian Society of Agriculture Engineers, Distinguished Service Certificate of Indian Society of Agriculture Engineers. And the area of expertise is membrane processing and microencapsulation of bioprocessing and design of meat processing equipment, intellectual property management. Sir's expertise in the field of microencapsulation and membrane processing is very vast experience. Sir publish so many papers in the respective topic. So my request to our today's speaker, Narsaiah sir, please deliver his lecture. Sir.
Good morning to all of you. Thanks, Dr. Khad, for a nice introduction. I will be sharing the screen now, and we will start the presentation. There is some problem. Not getting this is not activated. Share.
Burshiji,
Vaibhavji. Yes. Sir, there is share screen option is there in the bottom of.
No, it is coming your entire screen, and after that the share is not highlighted. That is inactive. This thing is.
Yes. Okay. Yes, sir. Yes.
This is fine.
Yes, sir.
Uh, okay. Good morning to all of you. It is great to connect with you. My video is coming.
Yes, sir.
Video.
Yes, sir. Yes, yes.
Okay. So I will be presenting on microencapsulation of bioactive ingredients. So if any of you have in between also, if you want, you can raise your hand and you can interrupt me if anything is needed. You need not wait till end for discussion. Uh, so we
I
will
think this
be
video is not this one. Start with
the
video.
microencapsulation of bioactive food ingredients is a way. What is microencapsulation? If we see the in microencapsulation, a core material or active ingredient is entrapped in a microcapsule. So the different configurations are given. One is a matrix microcapsule. Like in between this matrix, it is formed, and in between these, the core material is uh, encapsulated. Or hollow reservoir kind of thing, reservoir or hollow microcapsule. So you will have a hollow coating, and inside the bioactive ingredient are polynuclear or multi-core microcapsules where different nuclei are formed, and in each nuclei the core or active ingredient is encapsulated. Some hydrogel bead also, like different hydrogels are formed. We will see in our presentation also. We worked on this kind of hydrogels only. In those beads, the active ingredients are encapsulated. Or you have the liposomes or micelles, like multi-layer lamellar vesicle micelle. So these in this one, these are the hydrophobic and hydrophilic heads are there. These micelles are formed. So you can have, if two layers are there, then you can put hydrophilic components inside this. If hydrophobic components are there, that bioactive ingredient, then you can put it in these micelles are single layer vesicle or liposome. So the purpose of the microencapsulation is for immobilization of the active ingredient, or protecting the active ingredient from environmental factors, or you want to have a controlled release of the ingredient. So the when the ingredient is to be released, or structurizing, like if you take the stevia extract is there, that is extract, and you want to convert it into solid so that you can put in a tea bag, and some such kind of application you can use it. So that is called structurizing. You are changing the structure of the active ingredient. So if we historically see the the before, even before this historically carbonless paper or scratch we discussed, the best encapsulation is there in the nature. Like egg is the best example of micro encapsulation. Like you all know eggshell is there, and that shell has pores. So these pores and inside membrane, they act as a barrier to microbes and dust, as a but it allows the oxygen to go in, and carbon dioxide and moisture inside that to diffuse out. So this is the very good encapsulation example. Like it is the shell is there to give these properties as well as mechanical strength, and it should be easy enough for chick. Once the chick is hatched, it should be easy enough to break it and come out the chick. So it is a delicate balance that nature has evolved in such a case. That is, like we can say, that is the gold standard ideal case of encapsulation. Like it has many functions. The encapsulation, the eggshell is giving protection, mechanical strength, and barrier properties, as well as selective permeabilities. Like it will allow exchange of oxygen and from with carbon dioxide and moisture content from inside out, and oxygen from outside to in. And also it is protecting entry of bacteria and other things, so that the freshness of egg is maintained. So that is the ideal case, we can say. Or there are many other cases also, like if you take other example is pea pods, like mutter is there. If you see, this is coming in winter, like that is outside, so frosting is a problem in such conditions. To avoid that one, you have pod outside and inside the peas are there, and pea coating. So the gap between this piece and pea pod, that gives protection from frosting for the seed. So many examples are there. So taking that and we try to mimic those things in our applications. Like we will be doing very crudely compared to nature, but we will be taking those are the ideal cases are which we need to emulate from nature, how we can have such functionalities in our microcapsule. So the earliest applications are, if we see, the earlier we used to have carbon paper. Between two papers, we will put carbon paper, and on the top, if you write, the carbon on the carbon paper will make impression on the next page. So if that avoiding that paper, like on the back of your bill book or anywhere you want to make the copy, so on the back of it you put small microcapsules filled with the carbon ink. And when you write on the top, the on the bottom the microcapsules are broken and the carbon comes out and makes impression. Whatever you write on the next page, it will make a carbon copy. So that was the kind of 1960s, 50s, 60s. This came out, like, and then in the same period we had in magazines like scratch and sniff of flavors. Like if you give an advertisement in a magazine about flavors, so at the now we have the scratch cards are there. Similar to that one, a corner will be there where you put microcapsules filled with the flavors. So you read the advertisement, and if you want to experience the flavor, you scratch the corner where the microcapsules are broken and flavor is released. So you can have the feel of flavor also. These are the some early applications, and this is also widely used in drug delivery. Like for example, cancer is there. If you want to deliver the drug near to cancerous cells in chemotherapy, what happens, we give drug and it is systemic, so your hair will also be affected, or healthy cells, everything will be affected by the strong drugs. So to avoid those side effects, you need to target the targeted delivery of drug. Like the drug should go to cancerous cells only and kill cancerous cells only, avoiding the effect on the healthy cells. So in that case, you have functional groups which will on the microcapsules, which will go and bind to the cancerous cells and release the drug near to the cancerous cells. So that is one application. And nowadays you have the slow release aspirin or other tablets are coming, where you earlier we used to have burst release, like once you take everything active ingredient is released in one go, and whatever effect it is giving, that is giving, and other thing is inactivated by the body in enzymes and other chemicals in the our metabolic processes. The drug is inactivated, so you will have very short term relief, and next the drug is excreted. In slow release drugs, tablets, the drug is released slowly, so you will have the like painkillers or other things, it will have a for longer time, you will get the benefit, the effect will be there for longer time. So these are widely used. There are some examples in drug or medical field. So those things are taken, these applications are taken, and we have come to foods. Like from there we have taken some of the concepts and if we try to put them in food system. But in medicine, the margin is high. Like people will be ready to spend money when it comes to treatment, or when you are sick. You don't mind paying more for a specific drug, or if you have better feel or better quality. But in food, the margins will be less. So we have to optimize the cost effectiveness and the how much value you are giving by microencapsulation. Those things we have to consider. So, but we try to take some of the concepts from drugs only and try to make it in a cost effective way so that we can produce some functional foods. So the different polymers are which can be used as shell material for active ingredient to act as a shell material, like alginate, agarose, carrageenan, gelan gum, gelatin, chitosan, PLGA, polyvinyl alcohol, collagen, maltodextrins, and polyacrylamide. So these are some of the polymers that can be used as a shell material, that is outer covering or protective layer. And the various methods for producing these microcapsules are the encapsulated ingredients are spray drying, spray chilling, and spray cooling, air suspension coating, extrusion, centrifugal extrusion, freeze drying, co-preservation, spinning disc and co-crystallization, liposome entrapment, and interfacial polymerization. So some of these methods we will see in our presentation next slides. Before that, we will see like what we were discussing. You can do anything, encapsulation of many things, but where encapsulation should be adapted. So you should have definite advantage. Like it is widely used. We will take one or two cases where it is used, like probiotics. In probiotics, the it gives the microencapsulation gives additional protection to the probiotics, because probiotics are believed to provide good health benefits, and during storage also they need protection. So for improving the survival of probiotic practicals in storage, as well as when we take the food, incorporate in food, and when we take inside the gastrointestinal tract also, how the microencapsulation will provide you the protection, we will see. You can use in microencapsulation, you can add prebiotics also, or other food supplements also. You can put the advantage with microencapsulation is, along with probiotics, you can put prebiotics or other food supplements in the microcapsule. So you can dose them. So the advantage, if you see, this is the mouth and this is stomach. So the pH here is around 1.5 to 2, very high acidic pH. This is the design is such that whatever we take, it all the components have to be broken down into small molecular units. So that is the, so it is like a churning takes place in the highly acidic environment. So here the your food particles, whatever we chew, they will go and they will be broken into small components. So even if microorganisms or any thing is there, those are also broken down. But our goal is to protect the probiotics so that they go and they pass through this intestine, and in small intestine they colonize and give the beneficial effect. So we want to safely transport them from here to here. So if without encapsulation, the without protective cover, because of this acidic pH and the residence time in stomach, the microorganism, if you take, let us say, probiotics are defined as in the range of 10 to the power of 16 microorganisms are there in the food. So then you out of that, statistically very few will survive and go. But our aim is if we reduce the dose as well as increase the survival, even if we put 10 to the power of 3 or 4 microorganisms and make them to, most of them to survive and go to intestine and colonize there. So that is the our goal. So the encapsulation of probiotics in alginate provide that benefit, like it provides the uh, protection against this acidic environment as well as the churning mechanical stirring is there, the peristaltic action of stomach. So and once the capsules are there, the design is such that the here pH is 2, and when it is goes into intestine it is near neutral 7.5 7.4 or 7.2. So there the when the pH is changing, the microcapsules degrade and release the probiotics. So this is a in added advantage, like you are micro in probiotics. Generally probiotics are the very costly, like defined strains, probiotic strains are very costly, so you want to reduce the dose and cost of the probiotics and make them survive more. So this is an added advantage. So here you say that microencapsulation is providing a value to your product. Like without encapsulation, there was no survival or less survival, very minimal survival. With microencapsulation, you are having increasing the probability of survival. So this is one example where you say you should go for microencapsulation. So there are many things like microencapsulated ingredients. Mainly dairy products are there, where the probiotic bacteria are encapsulated and put in different dairy products. Even nowadays you get Yakult is there. So there also it is not encapsulated, but they put a very large number of probiotic microorganisms, and some of them will survive and give you the probiotic effect. So other widely used application is immobilization of enzymes. Like enzyme processes, you know, they are there in many processes. Even if you see your detergent powder, also the colored particles in your washing powder. So all those are enzymes. So in bioprocessing or biotechnology, if you immobilize the enzyme, it gives the different advantages. Like you can easily separate the enzymes from reaction mixture, because enzymes are a catalyst. They facilitate reaction, but they once the reaction is over, then you can take them out. Like you can reuse them. So if you don't encapsulate in the liquid form, they will be going with the products and they will be inactivated. But if you encapsulate it, you can separate them and reuse them in many batches, next batch and next batch, like in many reaction cycles. That will lower your cost of enzyme, as well as you can selective reactions. Like enzyme is there, so it is not accessible to all the things. Like only some of the substrates, if they are small, so they can diffuse into microcapsules and reaction will take place inside. So such selective reactions also you can have if other substrates are large and small substrate can be diffused through the your shell material or coating. So you can by immobilizing, you increase the stability of enzyme and you can control the reactions. Like you know where enzyme is there, you can control the reactions. So but the disadvantage is like free enzyme is a three-dimensional approach for the enzyme. Free enzyme, the advantage is the substrate can come from any direction, but in this encapsulated, the you will have restricted movement. So in different directions only it will come to the pores wherever they are available. And we are talking about smart processing. So some people define smart foods as these are the smart foods are those that have been developed with the invention of new or improved process. For example, some man-made materials or ingredients which are not natural, or natural ingredients which are not there in food, you are modifying them and putting them into uh, foods. So the smart foods have a function other than just providing energy or nutrients. It will have additional function, and this it particular function is not available in conventional foods. So these have been developed for specific applications, but some eventually became widespread, and in general use they have come. So, like some of the examples you can see, modified starches are functional foods like cholesterol reducing spreads, or probiotic yogurts, or fortified eggs, or meat analogs like texturized vegetable protein or mycoprotein, or you put encapsulated flavors in confectionery. Like you have nowadays 2-3 bursts of flavors in center fresh, or those kind of confectionery items. So initially it will be tasting sweet and other thing. Once it reaches core, the other flavors are released. So in one go you will have 2-3 experiences in one confectionery item. Like modern biotechnology, you can you genetically modify soybean or tomato plant, or rice, golden rice kind of thing. So those are also smart foods, but our focus will be like you one of the things is you can put non-compatible ingredients also into foods. Like if you encapsulate it and put it in the food, you can have otherwise not possible to incorporate, but by encapsulation you can put them. So the other analogy, if you want to simply understand, if we can compare the phones, now we have smartphones, so how they evolved. Similarly, how we are going in foods. The analogy, if we take earlier in 1940s, 50s, you have wireless or cordless phones with minimum buttons, and you can make call from here. Then additionally display and other functions increased, and more and more functions increased, and the size is getting reduced, the power consumed is getting reduced, they are becoming handy and convenient, and gradually the functions are increasing. Like when you have recall buttons here, now you have a display, and you can program them, and you can have different menu settings are there. In this one you can recall, and you can have contact lists and many calendar and other things, games you can put. So nowadays the smartphone has become an extended arm. Like you, without that you can't live nowadays. If your phone is broken down, if you have to give it in service center for 1 or 2 days, you will feel miserable, because it has your health you can check, you can play games, you can it has replaced your watch or many other gadgets. It has replaced only single, with single item you have multi functions. So this is the kind of evolution you see in the telephone, smartphones, as you see. Similarly, in foods, you see, earliest we used to cook, and then cooked foods packed in these thing, earlier thing. Then you have processed or ready to eat and ready to cook uh, foods have come, and now you are putting health, nutraceutical, and designer foods. And the focus is now, because of this COVID pandemic, now people are interested in foods which have immune boosting foods. So even Ayush, they are advocating the different foods, as well as like rasam or other things which boost immunity. as well as the other advisories. So many people are looking at food to enhance their immunity. So here we in foods we haven't reached this level. In the phone we, because this is the innovations follow Moore's law, like in smaller and smaller space they are putting more and more features. But in food we are still moving towards that one. Like we are now putting, let us say, curcumin is there, or lutein is there, antioxidants, or ginger extracts. So those things you can put in some foods. But if you want to have a single food, like people are looking at it a vending machine, given your data, your genome data, or your personal details, if you feed, it will personalize your diet, like depending on your body requirement, your genetic makeup, and your health records. It will design a food, like what proteins, what vitamins, and what are the advised ingredients. So mix them and make a designer food for you. And once you put your pay the thing, it will dispense the designer food to you. So that is where the smart foods are going, and encapsulation can play a great role here. Like here, if you want to put 10-20 ingredients in a one recipe, it is not possible with traditional way. Like only most of the ingredients need to be encapsulated so that they go into a single food. So the microencapsulation, if you see, it is a multidisciplinary approach is needed. Like you need to have a fusion of biology, chemistry, and engineering. So many other sciences are there, but these are major things which play critical role in encapsulation. Like biology, you see the viability of probiotics or living organisms, or bioavailability of the ingredient. So how it is providing effectiveness in your body system. All those things come from biology. If you have encapsulated ingredient and unencapsulated ingredient, how this is varying, the you need to have biology contribution here, biological sciences. Then you have chemistry. Like in encapsulation, if you want to produce those microcapsules, chemistry plays a major role in many processes, like many encapsulation processes. Like what we worked, or we are going to discuss, ion changing, so that at ambient temperature the liquid is converted into solid. So that is inotropic gelation is one example, or coacervation is there, other many other processes where chemistry plays a important role. And engineering, like if you want to produce the microcapsules, once you mix them, mix the ingredients and shell material and core material, you want to break them into small droplets. How you get microcapsules? So one of the way is to produce a jet with which can be broken into small droplets like a spray. So the force needed are the ways to get that spray or small droplets of uniform size. So engineering is there. So all these things, like major points I am covering, like many other things are there. The design of complete system needs all these inputs from you need to have a, each member need to appreciate the contribution of other sciences. Like you should have aptitude and attitude to incorporate all these views into one product, then only your encapsulation becomes successful. So one of the goals we are saying, like control release of ingredients. So there are generalized graph we have made, like burst release is there, this one. Then you have a zero order release, then you have first order release, and then you have trigger release. So we will see in burst release, like what we discussed earlier, a drug is there. So once the tablet is broken, a capsule or tablet, so everything disperses and 100% of drug is delivered here. So it will give immediate relief, but rest of the thing will be inactivated. The at zero time, the almost at zero time, 100% of active ingredient is released, and the whatever body absorbs 10, 20%, 30%, and rest 60, 70% or 80% is inactivated as it goes through the gastrointestinal tract. Similarly, if you see zero order means there is the release is continuous without any change with time. So for each 5 minutes or 5 seconds, your 20% is released. Next 10 seconds, 20 plus 20, 40 is released. 15, 60. So for each 5 minutes, you are releasing around 20% of the ingredient. So by 20 minutes, you reach up to 100%. So this is zero order means there is your capsule is behaving is such that it doesn't have any effect. Like continuously it is releasing, but it is slowly releasing. Like compared to burst release, the aspirin tablet, earlier aspirin tablet, if you take, it will be giving relief for, let us say, 5 to 10 minutes only. It is releasing and it will giving. But after that, the drug effect is wearing off, and you will be symptoms will be again there. But if you have a slow released one, the body is able to absorb only 20 to 30 in 5 minutes. So you are releasing around 20 to 30% of ingredient in 5 minutes, and next to 5 minutes 20 to 30 percent, 20%. So similarly, for 25 to 30 minutes, the drug is released slowly. So you will have its effect on a slow release. Like this is here, it is shown on a time scale of 20 minutes, but it will be maybe up to 5 to 10 hours. The slow release aspirin compared to burst release aspirin, if you take burst release aspirin, will give you relief for half an hour or 1 hour, and the slow release aspirin, where the aspirin is released slowly as for zero order, you will get the relief up to uh, 6, 7 hours or 8 hours, 10 hours. So that is the kind of advantage. And in first order or multiple order release, initially the release will be more, and then you will have slow release. Like if you, let us say, the example of our food is there. Like if you have contamination in the food, you have detected contamination, so you need a large amount of antibacterial or bactericide released initially. So this release pattern we would like, we will design the matrix material in such a way that initially it will release most of it, so that the contamination or majority of bacteria are killed in the first go, and after that slow release, incremental release will be slow, so that if additional contamination is there or residuals are there, this slow release will contain that one or inhibit the growth of that bacteria. So depending on your this thing, like what is the purpose, you can choose this application. Or if the contamination is more and you want instantaneous release of 100% to immediately kill, so you have a trigger release. Like there is a in capsule it is there, and after some time when you detect the your contamination or there in the food, let us say that example, so you want to release 100% of it in at that instant. So you make a trigger and let the capsule burst, and all the contents will be released, and it will give the desired action at that point, so that you will inactivate the like if you have pathogens are there, these are the spoilage organisms. If you suspect target the pathogens, so you don't want any residual to be there in the food, so you release a trigger release is there, like it is from revolver, you pull a trigger and bullet will be released, like that your antibacterial load will be released in one go and kill the pathogens in instantaneously. So so you need to see the purpose, and based on that you design the matrix or the shell material so that it gives the desired release pattern. So the release triggers are there, like pH, mechanical stress, or enzymes. Like pH is what we have discussed in microorganisms. Like in foods, it is the pH is an acidic side. Most of the processed foods, fruits, and other things. So the when microorganisms grow, that pH goes to neutral level or above the alkaline side. So you design your matrix material such that it will be intact in low pH, like alginate what we see, and if it goes into alkaline region or neutral to alkaline region, the contents are released and the microorganisms are killed. So this could be a pH as a trigger there, like your matrix is such that changes of pH will bring about release of the ingredients. Or mechanical stress, like shearing, if you detect something and if you start shearing, the microcapsules are broken, like what we have seen in the carbon paper or other things. As soon as you apply mechanical stress, the microcapsules are broken and the release takes place. Similarly, enzymes, you can have this also as a trigger, like you release enzyme depending on the, and in the matrix material you have substrate, so that it goes and attacks the matrix material and releases the contents. Or ultrasound, from outside, if you want to send a signal, ultrasound is energy input. If you give and you break the matrix is such that it is sensitive to ultrasound and it releases the contents. Or you can have temperature as the trigger, like the wall material will melt and release the components. Or ionic strength, this is also in biological systems. The ionic strength is one of the important factor. So you can manipulate the ionic strength to release the active ingredients. Or light also, sometimes you can have laser light. This is also from in the form of laser, you put in energy input you give, and you burst the microcapsules to release the ingredients. So these are the goals. This is taken from Bucci's presentation. They show this as the what are the goals of microencapsulation. Like you can have, as we discussed in case of enzymes, you if you want to have stability against shear force in a bioreactor, or in storage while moving the product and transportation. If you want to provide stability, so that you provide a mechanical strength to the active ingredient, and storage is better. And protection from environment or immune system, like protection from environment means ambient temperature, light, or humidity. If your ingredient are sensitive to those, you can encapsulate them. Or immune system, like in our body, whenever foreign matter goes, the immune system responds and sends the immune antibodies. So to protect the ingredients against the immune system, you can put a protective cover. Similarly, if you want to have control release, like what we have discussed in case of cancer, similar control release you can have in in our probiotics also, we wanted that the control release should be there in the intestine, not in the stomach. So such kind of things you can have for drugs or trigger release of flavors. Like in confectionery also, at the end you will get once you outer confectionery you have flavored confectionery. You eat it, and once that flavor is wearing off, if you chew it, the from center you will get another flavor. So such kind of things you can have that as a goal, or coating with functional groups like in cancerous cells you put a functional group which can attach to cancerous cells on the coating. Similarly, in functional foods also you can put functional groups on the coating so that it can give functionality to the microcapsule. Immobilization, we have already seen enzyme for biotransformation, probiotics, or even yeast also for to produce continuous bioreactors. Dosage and storage, so improves handling safety. So this is also, as we discussed, if we have high value ingredient like probiotics or lutein is there, that is very highly costly ingredient. Dosing them will be, they will be in few milligrams or nanograms. They have to be incorporated. So if you encapsulate them, otherwise it will be, dosing will be very difficult at that low level. So if you encapsulate, then it will gives a bulk this thing. Like you can count the capsules and put them. Like in each capsule, how much lutein is there or how much probiotics are there, and that way you can control the cost as well as storage. Like it is easy to store in the form of microcapsules rather than liquid extracts like stevia or other things. So depending on the goal, you will choose the wall material and what functionalities you want to increase. Like depending on the control release pattern you want, you have to put either, if you enzyme you are using as the substrate. So along with wall material, in the wall material you put a substrate, substantial portion of substrate, so that enzyme comes and attacks the substrate here, and the active ingredients are released. So all these things you have to keep in this in mind when you are going for microencapsulation. So what is your goal and how you are going to achieve that? So this we have all discussed the advantages in different examples: conversion of liquids to solids, or alteration of colloidal properties, sustained release, target release, taste and odor masking. Like this is a major one. We know that fish oil is good. Omega-3 fatty acids are there. It is good for health, but you don't like the odor. So if you encapsulate them, like putting the 2-3 locks on the fish oil and putting them in the food, so that your odor is masked. When you are taking, you don't get fishy smell, and you will once you it goes into stomach, and after stomach it releases in the intestine, so you will get the benefit. Similarly, let us say bitter taste compounds are there, like your curry or cooker beets. So extracts are there. They are tasting bitter. So children especially don't like those tastes. So if you encapsulate them and mask the taste, so that in their toffees or in their cakes, or which people like in fast food, you can put those things encapsulated and mask the taste, so that the kids will love the food. So this gives a new formulation concepts for functional foods. Like it will give additional degree of freedom, like where otherwise those ingredients cannot be incorporated in food, but by encapsulation you will get freedom of incorporating them in any kind of food. Many, not any, but many kinds of food you can put the encapsulated ingredients. So these are the applications in food and feed, like aromas, probiotics, bacteriocides, the omega-3 fatty acid or unsaturated fats, enzymes, and preservatives. In biotechnology, immobilization of cells, enzymes, or biosensor probes, or tissue culture, you can use encapsulation. In agriculture, you can use fungicides or bioremediation or biopesticides. In medicine, like control release or taste masking and artificial organs. So these are the some list, general list, but there are many applications. You can use encapsulation in many places in many fields. But the ultimately you remember what value it is providing and whether who is going to pay for that value, whether people are ready to pay for that functionality by encapsulating what you are offering additional function. So these are the some of the methods we have already seen, and we will briefly see some of the methods, and we will cover more on what methods out of these we have used, one or two methods, and some applications what we have encapsulated and put it in food or other applications we will see in subsequent slides. Like spray drying, this is most widely used. It is used mainly for flavors and fragrances or oils. So you know the spray dryer, you take the core material in this one. Core particles are dispersed in a polymer solution. Like generally the polymer is maltodextrin is taken, that is because it is a easy to make powder, it gives good flowability properties and easily spray can be sprayed, right? So maltodextrin is invariably used for encapsulation application by spray drying. So in that one or in other powders also, like if you want to make tamarind powder or other powders where you want to increase the solids, there also you put the maltodextrin in those things so that you get a flowable powder. Not only encapsulated, but other applications also where otherwise you will get a sticky or the hygroscopic compounds. So you can get a porous and flowable property by incorporating this maltodextrin. So the shell material solidifies into core materials, and as the water evaporates, the core material, whatever flavors or oils, they absorb onto the porous space of these spray dried particles. So these are polynuclear or matrix type, what we have discussed in first second slide. So either different nuclei are there, or matrix kind of thing is there. So in the on the matrix, the flavors, oils, or fragrances are absorbed. So that is the thing. This is the spray dryer, you all know. This is the drying chamber. You are feeding them from here, and drying gas is heated here, and HEPA filter so that any particles or contaminants are removed here, and the drying gas, the particle, the feed is fed from the feed pump through the nozzle, and it is made into small droplets. So from the droplet, the air goes in and heats the droplets, and the solvent is evaporated. So some people they ask like why the temperature here it is 130, but still spray drying can be used for heat sensitive ingredients also, because in actual droplet the temperature is not going more than 60 or 70 degrees or so. So the here 120 130 is there, but for a short time the particle will be there in the chamber, and during this time, because the surface area is more, the droplet is small, and evaporation takes place faster, and while evaporation is taking place, so this is gets cooled because of evaporative cooling type of effect. So the powder particle temperature won't go into 130 degrees Celsius, but it is remains in a range of 60 70 or 50 to 60. So if you use 130 or 140 degrees Celsius as heating air, so that's why you can use this for even heat sensitive ingredients also for encapsulation. So these water is evaporated and the in cyclone the particles are bigger particles are separated and finer particles are separated using bag filter. So spray cooling or spray congealing is similar to this one. Instead of heating here, you refrigerate or cool the air here so that hot melt is fed from this one and it is melting waxes or honeybee wax or other waxes. You melt them at around 60, 70 degrees or 80 degrees where they are liquid along with core material. The wax is heated and the core materials are mixed and they at 70, 80 degrees this is sprayed, and here instead of heating you send a cool gas so that the temperature is reduced to 30, 40 degrees for these droplets. So these droplets instantaneously solidify and the ingredients in that wax or molten material is solidified and encapsulated. So that is the spray congealing. You can see this is a fluid bed suspended coating suspension method is there. This is mainly used for pharmaceutical. In the pharmaceutical industry, the coating material is sprayed from top and the particles are fluidized, the particle coating on which coating needs to be done. So like what we said, the functional groups need to be added to the coating. So here the coating material is also very costly. So this equipment is costly, like Worcester or Worcester process it is called. This equipment pilot scale itself will cost some 60, 70 lakhs. So when you have even coating material also as a high value coating material, very thin layer of coating, when in a controlled way, if you want to coat the particles, you can have this fluidized bed or air suspension method of coating. Like from here, air will be coming and fluidizing the particles, and spray is coming from top, or you can spray from side also, from bottom. So you can have different configurations. And nozzle extrusion are this is the mechanical or physical method. In this one you apply force to the either through pressurized pump or air pressure to produce the capsules. So drilling is these three four methods are there. Simple dripping with a concentric air jet, electrostatic encapsulation, and rotating disc. So we will see these things in subsequent slides. Like what is the simple dripping is, like this is in many labs for encapsulation they use as a preliminary for preliminary studies or feasibility. If they want to see, you prepare the uh, generally alginate based system they use. Like the alginate is there and it is pumped through the nozzle by or you put it here through gravity, it is flowing through the nozzle, and it is simple droplets are falling, and here reaction is taking place and microcapsules. These are not microcapsules, but these are beads in the size of 2 to 5 mm. A concentric air jet. Like this principle, based on this we developed encapsulators, two encapsulators we will show. So this is the simple way to represent it is you are putting the matrix material or shell material here along with the core material, and as a jet it is coming through this nozzle. You are either pumping it to the peristaltic pump or syringe pump, and compressed air is coming from another nozzle and breaking this jet into small droplets. So and it is falling into a reaction path here, and the reaction is taking place. You have a magnetic stirrer so that it stirs and the reaction is taking place in a faster way. So diameter is in the range of 100 to 200 micron. So this method we will see in detail some of the equipment using this way of doing the encapsulation. The other one is electrostatic encapsulation. So you have a capillary or orifice nozzle here, and the you put electric charge on the nozzle and in the broth, so reaction broth, and you apply a high voltage across this one, and this high voltage is the reaction on and off, like it will be uh, creating a pull from here. Like when you apply voltage, the liquid is positively charged here because it is coming here, the and the here it is negatively charged. So the pull from when you apply high voltage, when the gap is less, this jet is dragged from this nozzle into the reaction broth, and after that you will put off the voltage, then it stops, then again you put apply voltage. Similarly you do this per second in thousands of times, like voltage is applied and disengaged in intermittent way, so that depending on the frequency of variation the droplet size will be varying. So this is the commercially available with NISCO is there, or this kind of thing. Even NASA also they have tried some experiments in space using this one, so that in space you can produce the microcapsules for some their experiments. So but here the capacity is very low, and you can have large range of viscosity, but the capacity will be low, and you can have 50 to 1000 micron depending on the size of RFIs you can vary, and you will get very uniform size because it is a controlled process. Each droplet is done by application of voltage, so you will get uniform size, but throughput will be very less. That is the major limitation. Similarly, jet cutter, like the jet is coming from the nozzle here, and a cutter is here, like it is a hollow this thing with the blades, like a circular one is there. Your jet is coming, and the blades are rotating. This is the edge ring. In between it is supported, but on this one some blades are put at each point, like in each quadrant, or maybe 6 or 8 blades are put, and as it is rotating the coming jet is cut by these blades, like this is the inner one, and this is your outer ring is there, and the blades are there. So depending on the rotation speed, the jet will be cutting the wire or blade is there. So this is like a your vegetable chopping. You are with the blade or wire, you are chopping the jet, so you will get the, but when you are moving the, as it is rotating, the droplet pathway is deflected, so you have to design your collection path in such a way that it can collect these droplets. So here you can't use for high viscosity solution, and you can use you can get 300 to 1000 micron. You can have high throughput and low dispersion in this case. So another one is like this was developed by Innotech, now taken over by Buki. They offer this based on this technology, the microencapsulator, that is called vibrating nozzle technology. So the here also dispersion is less. That means the size range is small, like 5 to 10% is the variation in size. Otherwise, all will be around 90% will be in the same size. You have high throughput, and you can have from 100 to 1000 micron the droplet sizes. You need low viscosity solutions only in this one, because as we will see the principle, the jet has to come through the nozzle freely. So you need to have low viscosity solutions only. So these are the components of the you have a syringe pump, the feeding from here, and vibrating nozzle here, and the alternator. This is vibrating the alternatively applying the voltage across the quartz crystalline, vibrating the nozzle, and a electrostatic dispersion unit will be there. We will see what is the advantage of having this one, and a sample cup to in between if you want to take samples whether the capsules are forming fine or not, you can move it into the path of the jet and you can collect the samples. And the mechanical stirrer or the stirrer will be there, and the reaction will take place for 20 minutes or so, and then you can harvest the capsules. The concentric nozzle is the same nozzle concept we can use, like it is physically showing actual this thing, like a sunflower oil with an anthocyanin colored one encapsulated in alginate. So here you have two nozzles. From inner nozzle you will be getting the sunflower oil with anthocyanin, and from other nozzle you will be getting the alginate. This is surrounding, and this nozzle is vibrating at high frequency. So the jet is coming, and due to the vibration of this jet it is broken down and the capsules are formed. You can see the how they are forming, like inside this one you can clearly see this is actual photograph that Bookie they have given this application. They have done this one, and real-time photography you can see. So here the core material is coming from here, shell material is coming, and alternator is there. So it is vibrating. So if you can see this in a detail. So this is close view of the capsule, you can see. So what happens is, in this one the principle is the jet is coming, and when the nozzle on the nozzle you are applying a quartz crystal is there and it is vibrating at that one. So due to that vibration the jet is also vibrating, and after due to relay fields like the laminar regime, when the flow is taking place in a streamlined way, when the jet is vibrating at certain frequency, after some time the due to viscous forces and gravity forces they are balancing here, but as it is going down the gravitational forces increase and they will pull down this from the jet, this droplet. So this is delicate balance of those viscous forces to gravity forces. So that principle you are getting. So that's why the dispersion is 5 to 10%. That size variation is very less. You will get uniform size capsules. So how these beads are formed, like in this one we are saying alginate is mostly used. Alginate or carrageenan is also works on the same principle. It has CONA, sodium alginate. This is alginate monomer unit. So multiple units of this is a polymer chain. The alginate is actually from surface layer of seaweed. This alginate is extracted, and it is in the form of sodium alginate. It is sodium ions are here on each unit. One sodium ion is there on each alginate monomer unit. So this is a long chain, and you are when you like this is if we see the sodium alginate is the here along with the your component or core material is here, it is falling in the form of sodium alginate. Here you are putting calcium chloride. This is the calcium chloride broth. So what happens is the sodium ions are replaced by calcium ion. Here we see this sodium ion is, if we graphically represent this chain as here one chain and another chain, adjacent chain as here. So Na molecule is here on this ridge, on this ridge, on this ridge. So one Na molecule on this one and one sodium molecule on adjacent chain. This is replaced by calcium ion. So calcium is divalent ion. So this is sodium is Na plus monovalent and calcium is divalent. So each calcium ion can replace two sodium ions. So this is divalent, but so it can bind to the one valency here and one valency on the next chain. So at many places, because the calcium chloride solution we are taking around 2 molar concentration, so many reactions are, these reactions are taking place and two sodium ions of adjacent cells, one here, one from here. So that way, if you see, three-dimensional matrix is forming, that hydrogel is forming of calcium alginate. Earlier it is sodium alginate, and once that into that broth, calcium broth, it form calcium chloride broth, it forms, the calcium ions replace sodium ions, and at ambient temperature sodium alginate is liquid form, and when they combine together, this reaction takes place, they become solidified. So you can get a hydrogel of calcium alginate. So using this one, we encapsulated yeast. So for using as fermentation initially, and we have encapsulated amla juice also, arginate plus starch and fresh amla juice. But because alginate has more bigger pores, ascorbic acid or in amla juice, the vitamin C is a small molecule, so only 15 to 20% is the encapsulation efficiency if you go for small molecule. Whereas yeast is a macromolecular bigger one, we could get 90% of encapsulation efficiency. Or if you control it properly, even you can go up to 100% with yeast or probiotics. So this is the droplet generator, initial droplet generator we made. From here, you with syringe, you put the alginate along with your core material, and compressed air is from the other one. So this was, as Dr. Kard was saying, giving introduction. I worked in before joining NDRI. I worked in industry, Vegan India Private Limited. There we used to design systems, steam jet based ejector, like thermo compressor and vapor compressor system. You must have studied in dairy or in food processing. So that is nothing but high pressure steam is coming, and it is entraining the low pressure vapors from here and compressing and releasing it to the atmosphere. So I had experience with handling these systems, like fluidic systems at high pressure, how they entrain and other things. So that experience I used to design a droplet generator, so that we have a microencapsulator with multiple air jet droplet generator. So here that droplet generator is here. So this we filed patent and we got patent for this one. With here you see multiple jets of air will be coming, around 4 jets from 4 directions. The at an angle, at let us say 60 degrees angle, the jet is coming, and from center the liquid jet is coming through the programmable peristaltic pump. Through central nozzle, the jet is coming, and from outer side, the 4 jets of compressed air. The compressed air is connected to the outer jet. So, and 4 openings are there. These 4 openings are angled towards the center. Like these, they will be coming at an angle from here to this one, from here, from four directions. They will be concentrating on the central jet coming from the peristaltic form. So that four jets break this single jet of alginate into small droplets, and you get and here you take the calcium chloride solution. The sodium alginate goes in here and reacts, and the sodium ions are replaced by calcium ion in this one, and this is a rotating mechanism is there. So you can get a with a dyno drive, you can control the speed of rotation, and you need pressure regulation. The pressure should be precisely regulated so that you can control the size of the microcapsule. So these are the, like, we use internal mixing and external mixing. Like the compressed air is coming from here, and the liquid or alginate jet is coming from here, and they are mixing here and coming out through the nozzle. This is internal mixing. Here the liquid jet is coming out of the nozzle, and then your compressed air is coming and mixing outside the nozzle. So this is called external mix to fluid jet. So we use sometimes this type of thing, and depending on the viscosity and application, you can have these types of nozzles to make the spray. So this we developed, and this is somewhere in 2010-11. After that, we conducted a paid training for industry, and from ITC, from Tata Chemicals, they came. They were interested in, like they said, this is fine, but we want to encapsulate the probiotic bacteria. Here it is open, so for aseptic processing, like probiotics, they will be contaminated. So we need a facility with aseptic processing facility. So for that one, we developed a new configuration with glass nozzles and autoclavable system. So there were three configurations of nozzles we will show, like single air inlet and this is a liquid jet inlet. So this is single air inlet nozzle. Then you have from here the alginate is coming, and from outer nozzle compressed air is coming. Here double air inlet jet glass nozzle. So the liquid is coming from here, and from two nozzles interconnected nozzles, from outer nozzle you have a air coming out, and then we had the dual air pressure glass nozzle. Like liquid is coming, and it is there are two nozzles, like one is outer nozzle and another one is inner air nozzle. Like compressed air is coming from here, and the liquid is coming, and inside it is broken, and in next stage a little higher pressure air pressure is coming from the outer nozzle, and whatever is broken in first stage, it is broken in second stage. That is like in two stages the breaking of the jet is taking place. Here you will get more uniform size, like whatever big droplets are there, they will also be broken in the second stage. So here double air pressure, like air here in this one, at same air pressure two inlets were there, but here we had two different pressures and two different nozzles in the same nozzle that was there, but here it is actually three concentric nozzles are there, one inside, then a low pressure air nozzle, and then high pressure air nozzle. So in first stage, the liquid is broken in inside, and then the outer nozzle in second stage it is broken down. So this is the complete system. Those are the nozzle configurations in this one. We got the patent, another patent. These two patents are there. So this was the answer to their problem. Like you can this is a glass-based nozzle autoclavable system. You can put this in autoclave and entire components can be uh, autoclave, and you can autoclave the pipes with either hydrogen peroxide or alcohol, or some of the pipes you can autoclave also along with this one nozzle, these parts, and then you can put in a aseptic environment or in laminar flow kind of thing in. You can do encapsulation of probiotics here. So magnetic stirrer is here, nozzle is here, and you compressed air is coming from the side, and the programmable peristaltic pump is there for pumping your uh, this alginate liquid. So we developed this clean room like HEPA with HEPA filter, and you can make a clean environment like this purifies the air, aeroside it is called. Whatever germs or bacteria and virus is there in the air, it is taken sucked in here, and inside the there are plasma state. They say this is from NASA, so the technology is there, but the air will be sterilized. If any bacteria is there or any microorganism is there, that is subjected to the plasma state molecules. So at high energy, those will be killed and the air is purified. So this NASA uses it for their where they want to maintain sterile environment in testing or in training or in space experiments. So that you can clean the air, and from outside which is coming through the HEPA filters it is coming, so you can maintain a aseptic environment to produce the microcapsules in clean condition, so that if you want to use for probiotics you can use this one. And some applications what we have done, I will rush through these things. uh, Pidiocin is the antimicrobial compound which was put in liposomes and then put in alginate, so hybrid microcapsules, and its control release pidiocin to control the contamination. This is using phosphatidylcholine as emulsifier and lecithin as emulsifier. So if you see, phosphatidylcholine is giving better control. Like if it is releases more and sustained, the antibacterial action in the terms of colony forming units we have evaluated. So in without this one, it is coming to 10 to the power of 11 to 12 in 72 hours. But if you have pidiocin without encapsulation, it is coming to 10 to the power of 8. With the lecithin, it is coming to, ultimately it's coming but the on lower side. But up to 10 12 days, it is below acceptable level when you are using phosphatidylcholine. So these are the different combinations. The optimized conditions are like 2.5% sodium alginate, 0.34% guar gum, and 2% pectin, and 0.17% phosphatidylcholine. You will get around 75% encapsulation of pidiocin. This is the optimum, and using this one we have seen different combinations around optimum value, and how it is affecting the clear zone. If you take this zone and this zone, very small clear zone is there, but here you can get C6 and C8, you will get very good combination uh, encapsulation efficiency as well as clear zone. So here also the same for CFUs we have seen like C6 combination plus direct pidiocin. If you add initial releases, the burst releases there, and then this one your control release, it will give up to 12 days. This 12 to 16 days you can have safe storage. Then if you encapsulated capsules, if you put this is the zone of the indicator organism, Listeria monocytosis pathogen is there. If you put these capsules, so around these capsules you see clear zone, that is it is releasing the pyriocin, and you can see the clear zone. This was up to 9 days the clear zone was there, and after that it is clear zone reduced further. That means you can say the capsules can release up to 9 to 10 days. The release is effective, and it is effective against the microorganisms. Similarly, this we have seen in paneer. So, different concentrations of pyriocin, international units 500,000. But all these are the total count generally should be 1000, 10 to the power of 3 or less. So it is more than that. So we with these concentrations, even initial itself it is high, and it is gradually increasing. Though if you increase the total count is less, but still it is above the acceptable level. If we increase the IUs to 3000, 4000, 5000, and if you see from 4000 onwards, even 3000 also, up to 6 days, 7 days, this is uh, in the acceptable region. Less to the power, 10 to the power of 3 or less than 1000 colonies in total count, up to 9 days. Similarly, we tried to use it for meat, but in meat is a very good medium for growth of microorganisms. The nutrients are there. Even with pyriocin, even up to 10,000 units also, it was quite high, and we don't recommend that for meat. But paneer, you can consider it. It is effective. And we have used for minimally processed fruits like papaya, coating with alginate incorporated pyriocin. So this also, the main problem is one is bacterial is not a problem, but it loses texture. The papaya pieces, once you cut, they become firmness is decreased, and they become squishy after 1 or 2 or 3 days. So by putting this, you can give protection against microbes, as well as you can preserve the texture also. So the gas compositions with this, because we are providing a coating, so it is modifying the atmosphere in the headspace. CO2 is increasing, O2 is decreasing, and you TSS concentrations variations you can see. So it is like whatever edible coatings, even without the algae pyriocin, also it can give the texture retention. You can see firmness. Uh, the control is losing after 3 days. The firmness should be more than 3 newtons for acceptable region. The control is after 3 days. It is if you keep outside or in fridge without this thing, it will lose the texture. 1%, 2 and 1.5% and 2% with pyriocin and without pyriocin, with bacteriocin and without bacteriocin. You can see the 2% will retain up to 20 days. That is more than sufficient. If you cut the pieces, maybe 4 5 days is the shelf life you are looking at. But if you are minimally processed point from processing to selling, even up to maybe 10 12 or 15 days, the firmness is retained. If you minimally process and coat with alginate, you can have even without pyriocin also, it is giving reasonably good. With pyriocin, it is still further better. So, but the conclusion is, if any bacteria is there, it will give protection, as well as If you don't want that, also even simple coating also can give firmness, retain firmness with 2% alginate coating. So total plate count, you can see it is up to 9 days. It is 9 or 12 days. It is acceptable, less than 1000 for 2% with bacteriocin. And we used it for flaxseed oil, garlic oil, and fish oil in soya lecithin, and make this emulsion, and then blend with this sodium alginate and make microcapsules. So these microcapsules we have put in bread. We have characterized the emulsion like it is shear thinning emulsions what we make with garlic oil, alginate, and fish oil or fish oil and flaxseed oil. All these are shear thinning fluids, and the range is the 200 nanometer particle size is there for those droplets. And this is for flaxseed oil. Same thing we have done. And the capsules, if you see, fish oil microcapsules, fish oil plus garlic oil, and garlic oil plus flaxseed oil microcapsules. So these are there is a color difference, but all the colors are acceptable, good, appealing in color. And this is the size from microscope image. We can measure the sizes of the capsules, and color we have seen how the color is changing. Encapsulation efficiency, these are the from 70 to 90% for different this thing. What we observed is like when you have fish oil plus garlic oil or flaxseed plus garlic oil, this is having synergistic effect. Like only fish oil it is 70%, or only flaxseed oil it is 80%, 85% encapsulation efficiency. But if you mix them, there is synergistic effect. Like it is going to 92% in both cases, because when the oils are mixed together, they will form emulsions, and the encapsulation efficiency increases. They hold one another together because they are in liquid. The fats come together, so the encapsulation efficiency increases. So FTIR to characterize these capsules. So once you the major thing is once you encapsulate, you characterize the capsules for size, then morphology, then chemical characterization using the components, whether that components are there in the capsule, is there any interaction. So those things you can see using FTIR. These in pure and in capsule, at what wavelengths the vibrations are there, peaks and signature peaks are there, you can see. uh, this you need lot of time to match this one with the flaxseed oil here and flaxseed oil here, the same at same wavelengths you can get the match the how they are getting the peaks. And this is the same image, so that you can morphology on surface as well as in cross section, because these are the droplets due to oil droplets. This is the voids are formed, and in control the compared to these indentations are deformities are there in control sample. The more uniform this thing is there in the oil, garlic oil or fish oil. So swelling index, you have to characterize the products as well as like what whenever you are encapsulating, the first thing is you have to find the encapsulation efficiency, how much you have taken the core ingredient. Like in this case, if we say flaxseed oil, how much we have taken and how much we have got in the capsule. So that gives the encapsulation efficiency. That is the one actual loading of fish oil or garlic oil or flaxseed oil. That is what is there in the capsule divided by total fish oil we have taken for encapsulation. Total fish oil or total garlic oil or flaxseed oil. So that gives how much of your active component has gone into capsules. That is one indication, and then other physical and morphological characteristics you can see. And then you do release studies. These capsules you take in actual gastrointestinal studies. We have studied, but I am not showing. That is the other thing is how if it is put in food and if we take in our stomach, how it is released. Those simulated studies you can do. And sensory evaluation, if you see the smell is reduced in case of the fish oil uh, with this is the on 5-point hedonic scale. The appearance is same for all the things and color is also almost same, but the smell is it it is better for the sample 3. This is the sample 3 is better. Similarly, you can see for flaxseed oil also. It is that means it is giving a masking order, and we measure the this oxidation is a problem. So antioxidant property, that how much by encapsulation you can get less rancidity for longer storage period. That also we evaluated, and we have put them in the bread. These microcapsules of flaxseed oil and fish oil, and you can see this is the close up of the bread fortified with garlic oil, flaxseed oil, and flaxseed plus garlic oil. And this is sensory scores. Above 6 is acceptable. So these all these are acceptable range only. You can encapsulate bread with either flaxseed oil or fish oil. This is for flaxseed oil. The flaxseed plus garlic oil, they are acceptable for even up to 7 days. Generally, the bread shelf life is 5 to 6 days, so even up to 7 days, the sensory quality is better. So if you store it well, with it will be giving the benefit of these flaxseed oil or fish oil, but along with shelf life of 7 days without any compromise in for the sensory score. Thank you. So this is there, and if you have anything to discuss or want clarification, I am at your disposal.
Yeah. Thank you, sir, Narsaiah sir, for your nice presentation of microencapsulation. Uh, we have some questions in chat box, sir. Uh, can you take sir question?
Yeah.
Hello.
Anybody?
Yes. Mr. Aniket Jadhav has asked one question, sir. As we know, probiotics like Mr. Pratik Nyai. What about the encapsulation
Your audio
efficiency?
is not coming clearly. What was the question?
Yes, sir. I'm reading the question, sir. Question
Hmm.
from Pratik Nyai. What about the encapsulation efficiency and shelf life of micro-encapsulated food?
Encapsulation efficiency,
Sir, did you get?
you evaluate. Okay. Anything else? Micro encapsulation efficiency for many foods, what we have done, it is in the 75 to 80%. So depending on the this thing, the shelf life is dependent on mostly what we have to see is the generally encapsulated ingredients we want to incorporate, just produce just before the incorporation into making the food product. So the shelf life will be majorly determined by the shelf life of the food product. Now, the encapsulated ingredients are always having more shelf life more than the food there, but the limiting food shelf life will be the shelf life of the food product where these microcapsules are incorporated. So if like in bread, the limiting value is 6 to 7 days is the shelf life of bread. But if you can maintain the shelf life of bread up to 15 days also, our microcapsules will be stable up to 15-20 days also, no problem. So some acidity will be there that we have to check maybe up to 15-16 days. But for this period, 7 days for bread we have taken 7 days as the evaluation time. So that the normal bread life is they are giving 7 days. So our ingredient should have integrity up to 7 to 8 days minimum.
Okay, thank you, sir. Next question from Dr. Yudi Chavan, sir. What should be the storage condition for encapsulated food products?
Encapsulated ingredients you have to generally if you can put in if you have dried the microcapsules, you can put in LEP or HTP Ziplocs and you can put in refrigerated conditions, normal fridge. They will be stable. So if ingredient is light sensitive, then if it is not light sensitive and if you can control the moisture, you can pack them in a moisture barrier packaging and put outside also. The microcapsules won't have any problem. But if you want to retain the bioactive ingredient for longer time, it is better like you put in LEP or HDP and you can put in refrigerator. It will solve for many applications. That would be sufficient, more than sufficient.
Oh, thank you, sir. Next question from Dr. Bindu. Why only multinuclear type microcapsules are obtained in case of spray drying?
Uh, Microencapsulation and spray drying. What is the question? Can
Why
you
only multinuclear type microcapsules are obtained in case of spray drying?
in spray drying, what happens is like it is a porous like you must have seen carbonated the charcoal kind of application. If you have activated carbon, so it is a porous structure is formed. Like in spray drying, what happens is the water is evaporated from all directions, so you get a in powder. If you see the micro same of micro the powder particles, this will be a porous structure. So in that one, what happens is your when you mix your fragrance or other active ingredients with the maltodextrin or starch material, what happens is this starch matrix is forming that porous structure. The fragrance or the flavors which are there, they will be at multiple points, they will be absorbing. So that is called polynuclear. Like wherever that in the droplet itself, at different points, that fragrance or flavor will be absorbed onto that porous structure. So that's why it is called polynuclear. Because in spray drying, you don't get a hollow sphere and inside that one a defined structure you won't get. You will get a porous structure like charcoal or activated carbon. If you see images, or through if you search the Google same image of spray dried powders, it will be porous structure. So on that at multiple locations, your fragrance or flavor will be absorbed as a at each point one nucleus. So that is called polynuclear. I guess it is clear, or if you further
Yeah, yes, sir. Yes, yes, yes. Thank you,
clarification.
sir. Next question from Himani Singh. How to microencapsules encapsulate the essential oils of spices and which methods can be used?
Ginger oil, encapsulation of ginger oil.
Okay, and which methods can be used, sir?
Huh?
Which methods can be used for that micro encapsulation?
You, can you type if it is typed
Type, sir.
like
Question from Himani Singh.
Himani? Just one
Yes.
second.
Borshiji, read again.
Yes, I have on. Himani ma'am, I have unmuted you. Please ask your question. How to micro encapsulate the essential oils of spices and which methods can be used?
Hello,
Yes, ma'am.
can you
Yes,
hear
please.
me?
Yes,
Yeah.
please
Yes.
ask your question.
So my question is, I wanted to know that actually I'm working on spices. I'm a PhD scholar at NIFTM, and
Okay.
I want to encapsulate the essential of essential oil of my spice that I'm using. So until now, I'm not been able to identify which method should I use to encapsulate the essential oil.
What is the purpose where you want to go for application, because it is depends on the ultimate application. If you what I have shown is the same method you can use for flaxseed oil or this thing. There what we have done is we first made emulsion. You take an emulsifier like lecithin, soya lecithin or phosphatidylcholine, and
Yes.
then make an emulsion with water,
Okay.
this emulsifier and oil, so that the
Achha.
oil droplets, the essential oil or ginger oil, whatever spice essential oils you are extracting, you make
Yes.
emulsion of that one,
Hmm.
and this emulsion you take it to alginate solution. So
Okay.
this is kind of we call it hybrid encapsulation or dual encapsulation. Like you make emulsion, that itself is the emulsifier is surrounding that your oil, essential oil, and then
Yes.
you take this emulsion to alginate and mix it with, and you again put it in alginate droplets into calcium chloride, and then you get calcium alginate the emulsion droplets encapsulated in calcium alginate. So
Correct.
that gives that is one approach. But this is like if you want to use, where you want to use. We wanted to use it in bread, so we can put that capsules into bread dough and we can make the bread. So what your application is there, this essential oil where you want to put, that also you have to see what is the
Okay.
target application. Depending on
Okay.
that, you can choose the encapsulation method.
Okay, sir. Okay.
And if
Borshiji,
you further
Yes.
need, my email ID is there. You can contact me personally also, no problem. If
Yes, sir.
anything
Yes.
is there, I would be glad to help you in
So
encapsulation.
surely, even I would like to, contact you for this matter.
Okay.
Yes.
Borshiji,
Thank you so
last
much.
question.
Yes,
Last
yes.
question.
Last question, sir. Because of time constraint, we are taking last question, and most of the participants have asked this question, sir. Same. Last question from Ridesh Pandey. Cost of micro encapsulator and supplier in India. What is the cost of micro encapsulator and supplier in India?
Uh, you are about cost of a micro encapsulation system.
Yes, sir. Yes, yes. And supplier in India.
Okay.
Yeah. Most of the
Yeah, I have
participants have
shown.
asked same question.
Yeah, I will elaborate. Like the micro encapsulation system, which is commercially available, is Bookie. That we have shown that it gives very good capsules, like uniform size, and that is the no doubt it is good. But the cost is anywhere from depending on the features from 15, 18 lakhs to 25 lakhs, or in that range. That Bookie or Inotech principle based, the vibration nozzle based encapsulator costs you in that range. Like if you bare minimum, if you take maybe 15, 16 lakhs. Otherwise, if you go on increasing aseptic attachment and other things, it may go up to 20, 25 lakhs in that range. That is roughly. because that varies the time and their commercial considerations, but rough in that range. What we developed the two encapsulators we have licensed, they will be costing no doubt you will get some variation in particle sizes. You won't get a very uniform size with this, but for many applications, especially in food or this thing, size is not a very critical thing for us. We can tolerate the size variation. So what we developed a simple encapsulator. This will be costing you depending on features and what kind of configuration you want. Maybe around 4-5 lakhs to 6-7 lakhs for our system. And if you want, if somebody is there, a simple system setup, they want to produce a microcapsules, I can help them if budgetary constraint is there. Even if they have a magnetic stirrer and peristaltic pump, uh, that can be done, or even peristaltic pump also, if it can be dispensed and with gravity feeding, if you can do, you need a compressor, and if you need a magnetic stirrer. Magnetic stirrer around 15-20,000 and around 30-40,000 for the compressor. So if anybody want, then they have to buy nozzles, just open type of system. You can get in maybe 1 to 1.5 lakhs also. If they wish, I can help them to assemble that setup. But as a aseptic, the autoclavable system, if they want to buy for what we have licensed, it starts from somewhere around 4 lakhs or 4 to 5 lakhs.
Okay.
Thank you very much, sir, for your nice presentation. Very informative, and this topic is new for all the participant. Number of the participant appreciated and gives such a type of remarks in our chat box. So thank you once again from our cast team and from our all the participant. Thank you once again, sir. Borshiji.
Yes, sir. Thank you, sir.
Thank you.
Now,
Thank
yes,
you
sir.
all.
Now I request Dr. Yogita Stanap ma'am from PDK Akola to please present vote of thanks.
A warm and graceful morning to Dr. K. Narsaiah sir, organization committee, and all dignitaries and all the participants of this training program. It is my privilege to propose a vote of thanks and acknowledge the contribution of those who worked really hard to make this training program so much informative and successful in this pandemic situation. So thank you very much for this new topic and this informative topic. Thank you very much.
Welcome. And I thank all the organizers for giving me the opportunity to talk on this one and interact with the participants in this COVID time we are having. So virtually we can meet and we can do something good. Thank you.
Yeah, thank you, sir. Yes, sir. Shall we close?
Yes.
Okay. Yeah. So participant, please be there for the second session of this day on application of nanotechnology in smart food processing by Dr. N.J. Thakur, sir, who is former Dean, Faculty of Agri Engineering at BSKQ in Napoli. So please be there at 4 p.m. today. Thank you one and all.